function notation, as you might recall, means that it's a new style of writing that allows us to express an equation in a slightly different way. So we need to replace the y in, for example, y equals mx plus b with this new notation style that might look like that. Y equals to f of x. Okay, so rather than use of an equation table or graphs or words to refer to a function, we name the function and we use f of x, which we read as f of x, to represent y. So for instance, if we have the equation y equals to 2x plus 1, then we rewrite the y as f of x equals to 2x plus 1. Right? So that's function notation. We use this. F of x represents the y. It's standing in for the y. Okay? So the notation f of x does not mean that we multiply the f times the x. That's the most common mistake. This is not a variable. Right here, the f. The f is not a letter representing a number. That's what a variable like x is, or a variable like y is, right? It's an unknown value that's being represented by a letter, and usually our goal is to evaluate it at a certain point, or find characteristics about the relationship between the two. But in this case, the f is not a letter representing an unknown number. It is a letter representing an equation. It is the title of the equation, which is one of the benefits of function notation, because it allows us to refer to different equations, as we'll see in a second, based on the title, which is this name. Okay, so one good way to think about it is in terms of input-output, right? So if we have some sort of f of something in there, so whatever goes in here is the input. Right? Traditionally an x, but it could be a different variable. So some sort of independent value goes in there, the independent variable, and the answer is some sort of an output. Right? So you can think of it as input-output. So the input is the x, the output is traditionally the y, traditionally x and y. But in this book it could be a variety of characters. So this is true for any function. To find f of 4, we say we evaluate the function at f of 4. So if we wanted to say find f of 4, this means evaluate evaluate the function when x equals 4. Right? That's what this right here means. Find f of 4 means evaluate the function when x equals to 4. Okay, so for instance, evaluate f of x given as negative 4x plus 2 at 5. So if we are given f of x equals to negative 4x plus 2, and they want you to evaluate it at 5, that's the same thing as asking you to find f of 5. So we know that the x value is a 5. So we rewrite this as negative 4 times 5 plus 2, because the x was right there. Okay. So then we evaluate it and we get f of negative 5 equals to negative 20 plus 2. So f of negative 5 equals to negative 18. Good? Questions? No? So the benefit of function notations, one of the benefits, is that you get to label lots of different things. So for instance, you could be given all of these functions. F of x equals to 2x squared minus 3x. G of x. So you could be given these functions. F of x equals to 2x squared minus 3x. G of x equals to 4x minus 2 all over 5x minus 1. Or h of x equals to 3x minus 5. So we have 3 different equations, and they're titled by the letters f, g, and h. So when I ask find f of negative 2, then you know which one they're talking about. They're talking about the f1. So you know to go to the f1, replace all the x's with negative 2, and that's when you get, you simplify that and get your answer. when they say find g of 3, then we know which one they're referring to. So that's one of the benefits of this function notation. So for f of negative 2, I know I'm going to go to the f function, so I'm going to have 2 times negative 2 squared minus 3 times negative 2, right? The x is given as negative 2, so we go to the function and replace all the x's with negative 2, as many as there are. So here there are 2 of them, there could be more. And then we go ahead and simplify this, so this turns into 2 times 4 minus negative 6, which gives you 8 plus 6, which gives you 14. So we'd say that, kind of bring this down. So here's my final statement. F of negative 2 equals to 14. This means that the x is negative 2. And this means that traditionally the y, if we want to go back to f, x, and y notation, we're saying when the x is negative 2, the y is 14. But we'd rather just leave it this way. F of negative 2 is 14. Good? Questions? What about g of 3? G of 3. Then we go to the g function, and I can see that this is going to be 4 times 3 minus 2 divided by 5 times 3 minus 1. So g of 3 in the numerator, that's going to be 12 minus 2 is going to be 10. In the denominator is going to be 15 minus 1 is 14. And then we can reduce that and leave it as a fraction. G of 3 equals to 5 over 7. Right? So we would stop there, but if we're asked to interpret what this means, it means that when the x is a 3, the function, the g function, evaluates to 5/7. Right? In the x and y notation, it would be when the x is 3, the y is 5/7. Any questions? Good? Sort of? Kind of? No? No? Okay. So sometimes we're asked to evaluate at a number, as we just did. Sometimes we'll be asked to evaluate at a letter, like h of a. So find h of a, which is so simple that it's kind of confusing. Right? So when we evaluate at a number, it means we go to the h function and replace all the x's by whatever number is in there. Well, in this case, we're going to replace all the x's with whatever letter is in there. So in this case, we'd end up with 3a minus 5. And now there's nothing else to simplify, because you can't simplify that any further, so we're done. All we really did is replace the x's with a's. So it's such a simple thing that it's sometimes a little confusing. Good? Questions? There's really nothing else to do there. Replace the x's with the a and you're done. Good? For something a little bit more complicated, it might make a little more sense. Like what if we had this, h of a minus 2, then here we would go and do this. Right? So instead of replacing the x with just an a, we're going to replace it with a little equation of a minus 2. So this was 3x minus 5, now it's going to be 3 times a minus 2. And now this is something we can simplify just a little bit, because we can do a little bit of arithmetic. So then distribute combined line terms as best we can. So this would be 3a minus 6 minus 5. So we'd get 3a minus 11. H of a minus 2. H of a minus 2. Good? Questions, comments, issues? No. We can also do something like, how about f of a plus 3 minus h of a plus 1. Right, so now we can combine a little statement, a little mathematical expression involving two different functions evaluated at different results, at different values of x. So for the f function, the instructions are, give me a number, I'm going to square it, multiply it times 2, and then subtract 3 times the input value you gave me. But the input value is this. So for this part alone, it'll be 2 times a plus 3 squared minus 3 times a plus 3. Right? That's what this part is. Right? And then minus, and then this part, and this part is going to be 3 times a plus 1 minus 5. And I did something wrong, or something's gonna, what's wrong? Any thoughts? Shout it right out if you know. What did I do wrong? Or I'm missing something, I should say. So the way I wrote it, I'm going to end up with something wrong.
You're missing like a F or something?
Not really. This subtraction applies to the whole thing, right? All of it. Subtract all of it. But the way I wrote it, it's really only going to be subtract the first term. So I'm not really going to get to apply it to the last term. So you have to introduce brackets here or parentheses or something to show that this needs to be distributed amongst the whole thing. So really this ends up being a plus 5 at the end. That's what it needs to be. Otherwise you're going to be off. Okay, so just be careful with that. The minus applies to the whole thing. Okay, so now we've properly substituted it in. Here is the f of x function. The x's are being replaced by this. Here is the h of x function, and the x's in this case are being replaced by that. And now I can try and simplify it as best I can. Remember that this is that foiling thing, if you remember that. We'll revisit this down the road in chapter 6, I think. But for now, if you don't remember, I'll just put it off over here on the side. Let's put it over here. So I'll go over here and maybe not a space. That's okay, I'll do it here. So this is a plus 3 times a plus 3. That's what this means. A plus 3 times a plus 3. Minus 3 a plus 3. Okay. Minus, and then brackets, and I'll go ahead and distribute this. So, doing it in pieces. Okay, so here I'm going to FOIL all this out if you recall. So when you FOIL it, it'll look like this. We got to multiply the a's, a times 3, 3 times a, 3 times 3. So we end up with 2 times a squared, a times a, plus 3a, plus another 3a, plus a 9. Right? That part right there is how you FOIL this. So we just took care of this part right here, of squaring that thing. Minus 3a minus 9. Remember to distribute. Minus 3a minus 9. Minus, and I'm going to minus each of these. Minus 3a minus 3 plus 5. When you distribute this minus through those. Good? Questions, questions, questions? Okay, so now I'm going to distribute this 2. This 2 applies to everything inside this parentheses. So I'll end up with 2a squared plus 6a plus another 6a plus an 18 minus 3a minus a 9 minus a 3a minus a 3 plus a 5. And now lots of stuff can combine. Right? So nobody plays with the a squared. It's the only one of its kind. So that one just stays there. 2a squared. Now the a's, we have one here. 6a plus another 6a, that's 12a. Minus 3, minus another 3. Oh, okay. So minus 6, those kind of cancel with this. We end up with a plus 6a. Right? Plus 6a. So here's 12, but then there's minus 6. So we end up with positive 6a. Right? So we took care of all of these a's. We already took care of the a squared. The only thing left is the whole numbers, the constants. So we got plus 18 minus 9. So at this point we're at plus 9. Plus 6. 11. Plus 11. Any questions? No? 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 So, hopefully this part is just arithmetic and it's okay. This might be a little bit rusty for people if you forgot how to FOIL. We'll revisit that in chapter 6. But this is really the important part that we're covering, the function notation. So we went to the f function. We knew we were talking about the f function because it's got the name right there, f. The x is this. We went to the h function. The x, the input is that. So we can evaluate it at that point. Any questions? No? Good? Sort of? Kind of? All right, moving on. Okay, so in some input-output pairs of a function g are shown in the table. So sometimes you're given an equation and you ask to evaluate things. Sometimes you'll be given a table like this one. So here we have a table where we have some x's, and then instead of y's, they wrote g of x. That's okay. It's in place of y, we have the notation g of x. So it's the g function. So based on the table, we can evaluate things at those points. What is the domain of this function, the g function? Well, it's just the input values that they've given me. The domain is 3, 4, 5, 6, and 7. Right? What's the range? 12, 9, 8. And that's it. We wouldn't repeat them again, even though they appeared more than once. So those are the possible answers, an 8, a 9, or a 12. Those are the only possible outputs, right? That's the range. Okay, so find g of 7. Okay, so that means that the x is a 7. So we go on our table, find 7, there it is. So the answer is 12. We would say g of 7 is 12. Good. What about find x when g of x is 9? So which of those input values results in an output of 9? That's what they're asking you. So we're going to have to read it backwards. We go to the right, we see where the 9 is, and we get an input value of 4 or 6. So there are two possible input values. So x is got two possible answers. So we have g of 7 is equal to 12, and then we know that g of 4 is equal to 9, and we also know that g of 6 is also equal to 9. So, you know, what are the x values that give you a 9? Well, x equals to 4 or 6 is the answer to the second one. And here we got that the answer was that one. The first one. Any questions? No? 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 Okay. So sometimes you'll be given an equation like this one. Very similar to the previous one. F of x equals to 3/2 x minus 1. Find f of 4. So this means that the x is 4. So we evaluate it at 4. So f of 4 is going to be equal to 3/2 times 4 minus 1. We reduce this. That turns into a 6 minus 1. Right? 2 goes into 4 twice. And so this will be 6 minus 1, or 5. So f of 4 is 5. Good. What about the other one? It says find x when f of x equals to negative 4. So what should we replace the negative 4? How should we replace that into our function? We should write... What question?
Negative 4 equals 3 over 2x times 1.
Right, it's the output value, right? So it's negative 4 equals to 3/2 x minus 1. We're looking for the x value that will give you a final answer of negative 4. That's what that's asking us for. Find x when f of x equals to negative 4. And so now we solve for x. We add 1 to both sides. Plus 1 plus 1, we get to negative 3 equals to 3 over 2x. And now what do we do? Multiply by the reciprocal, right? So I know that if I multiply this whole thing by 2/3, the 3's cancel, the 2's cancel, multiply this side by 2/3. Oh, in this case, the 3's cancel as well. We end up with negative 2. Well, that's a negative there. Negative 2 equals to x. Good. Questions, comments, issues? No, no, no. We can check. Let's make sure that this is true, that it works out. Is it true that when we have 3 over 2 times negative 2 minus 1, is it true that that whole thing is going to be equal to negative 4? Right? Because that's what we're saying is the answer. Find the x value that gives you an output of negative 4. So here the negatives cancel, giving you negative 3 minus 1 equals to negative 4. And yep, that's true. So it does work. We did find the answer. Good? Questions, comments, issues? Questions, questions, questions? Okay, so we have that. Sometimes you'll be giving a picture for you to solve these things. So here's an example. We have this graph. The picture is given, the graph is given, the equation is not necessarily given. And in some cases, you know, we'll be asked to find the equation of the line. but sometimes we'll just be asked to evaluate things based on the picture. So these can go very quickly. Number 1, find f of 4. That means that the x is 4. So we go across to 4, we go up until we run into the function, go across, and we see that the answer is 3. So when x is 4, y is 3, traditionally y. Well, it is y-axis in this case. So f of 4 equals to 3. Good. F of 0 means that the x is a 0. So we go to x value of 0, go up, and we see that it's equal to 1. So 0, 1 is the y-intercept point. Or we just write down f of 0 equals to 1. Good? Good, good, good. What about number 3? Find x when f of x is negative 2. So now we kind of have to go backwards, right? The negative 2 is the y. So we find negative 2 along the y value of y-axis, and then go across until we run into our function, and then go up and see that x is about a negative 6. Okay, so for the first one we had f of 4 was equal to 3. For the second one we had that f of 0 equals to 1. For the third one we have that when x equals to negative 6, f of x equals to negative 2. That's kind of an ugly statement. Let me just jump to the thing. We're saying that f of negative 6 equals to negative 2. But we were asked to find the x value whose answer is negative 2, and we found that that x value was negative 6. Right? So for the last one, 4, find x when f of x is 0. So again, the y value is a 0. When is this thing going to cross the x-axis? And we see that the answer is negative 2. Negative 2 comma 0 is the x-intercept point. So that'll be our answer. So we'd say that f of negative 2 equals 0. Right? The y is the 0, the x is a negative 2. Any questions, 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 questions? No? So the dependent variable of the function f can be represented by the expression formed by writing the independent variable name within the parentheses. So the dependent variable is the result of, or is equal to f of the independent variable, and this is what we call function notation. So, definition for it. This is a nice explanation of it again. So the y is the dependent variable, and we're setting it equal to the function name, traditionally f, but it could be any letter, and then in parentheses, the independent variable, traditionally x. So here are your instructions. Using equations of linear models to make predictions. So first, when making a prediction about a dependent variable of a linear model, substitute a chosen value for the independent variable in the model, then solve for the dependent variable. When making a prediction about the independent variable of a linear model, substitute a chosen value for the dependent variable of the model, then solve for the independent variable. Right? So if you're solving, well, okay, so we'll see some examples. So to find a linear model, and make estimates of prediction, first we're going to create a scattergram, which we've done either by hand or with our calculator. Determine whether or not, whether there is a non-vertical line that comes close to the points, right, if it's approximately linear. Then we're going to choose 2 points such that when we connect those 2 points, that line makes a pretty good approximation. That's one way we're going to do it. Or I might just say use the linear regression function in your calculator to find that line. So once you do that, you're going to write it. So you're going to find the equation either by finding those 2 points and doing it by hand, or using your calculator. You can verify it by checking the points that are on your equation. So when you choose 2 points and draw the line or find the line that connects those 2 points, you can always double check that those 2 points really are on the line. The rest of the points through data might not necessarily be on the line, since it's just approximating it. And same thing when you use your calculator's regression model. It doesn't necessarily mean that any of the points are on the line. To check it, it would be good to use your calculator, graph the scattergram, and then draw in the equations of lines that you came up with, and make sure that it really does look like it makes a good approximation, and then we use those equations to answer some of the questions involving the particular situation you might be in. So, for instance, let's say we let P equal to negative 0.48T plus 71 be the equation that models the percentage P of American adults who smoke at T years since the year 1900. The table below shows the data. Okay, so we have some real-world information. 1970, 37.4% of American adults smoked. That's pretty high. By 1980, they went down to 33.2, then so on and so forth. By the year 2010, only 19.4% of adult Americans smoked. Okay, so they've already given us that equation right there. But if they didn't give it to you, how would you find it? Well, when they give it to you this way, they usually are referring to the regression one. So the one that they're giving you right there is the one that sort of encompasses all the known data. So why don't we use our calculator to find the regression, the regression function, linear regression function, using that data right there. Okay, so we want to graph these guys, create a scattergram, and then find the linear regression line for them. So I'll go through this real quick. You turn on your calculator, you get to some random screen, whatever it is, you hit quit, second quit to get out of there. Clear whatever's on your main screen. We're going to go to Stat, Edit, so hit Enter. Then we're going to clear whatever was previously on there. We don't need it anymore. So clear, Enter, highlight L2, hit Clear and Enter. And now we got to input these results. But these results, we never use the calendar years, right? So we got to convert them into T values, which in this case is the number of years since 1900. 1970 translates into 70 years past 1900. And then 1980 translates into 80 years past 1900. So then 90, then 100, then 110. Okay, and then we put the percentage values. So 37.4, enter, and 33.2, enter, 25.3, 23.1, enter, and then 19.4, enter. There we go. Okay, so to create the scattergram, first I'm going to go to y equals, make sure there's nothing there. So there's an equation right there that's going to create problems. If I want to save it for later, I can use my arrows, get to where it says y equals, hit enter. Do you see how it's dark right now? But if I hit enter and move away, the equal sign is no longer dark. It's been deactivated. It's no longer going to try and graph it, but I get to save it. Or if I'm just never going to use this equation again, I could just hit clear and delete the whole thing. Either way, you don't want any active equations on there right now. So next I'm going to hit stat plot. From this screen I can see that the first one's on, the other two are off. I can tell from here that it's a scattergram with x and y coordinates being in list 1 and list 2. And it's graphing little plus symbols. I can already tell that's what I want. But if I wanted to change something, you would select enter and then change it. So I do want scattergram L1, L2. Everything looks good there. So next I'm going to go over to my window and choose a particular window that I would like to use for this information. In this case, I was going from input values of 70 to 110, so I know this is not going to do it for me. So maybe from 0 to 120 maybe would cover it. We'll see. And then the output values, these are going from 37 to 19, so negative 50 to 1,300 isn't going to cut it either. So let's make it from, I don't know, how about 0 to 100 to cover all the percentages, from 0 to 100%. Okay, and now I can hit graph, and there's my scattergram. So way out here, it started to kind of decline. I could see that it's on the decline, and it almost sort of looks like it's a straight line. So let's ask our calculator to come up with a line approximation to all those, a linear regression line that's a linear approximation of all of those. To do that, we go to Stat, go to the right under Calculate, go down to lin reg ax plus b, enter. Then I'm going to put parentheses L1, comma, L2, comma, and then this is where we do that vars thing. Vars, go to the right, enter, choose where you want to save it. Be careful not to delete something that you want to keep from, a prior case. So I'm going to put it in y sub 4, close parentheses, enter. And remember, some of you guys have that other screen, and you just walk through those steps. Where's the x coordinates? Where are the y coordinates? Where do you want to store it? Calculate, be done. Okay, so this is the linear regression line. It gives you an approximate slope of negative 0.49461 and a y-intercept of approximately 69.17. So if we look over here, it's somewhat close to the one they've given you here. Not incredibly close. I mean, if we round it to 2 decimal places, this would be 0.46. They had negative 0.48. This is negative 0.46. And the y-intercept we're getting is 69.17. They were just giving you 71. So somewhat close, but not exactly the same. Okay. And if we go over to y equals, we'll see that that equation has already been saved in y sub 4. And if we hit graph, it'll be the line that, and we get the line and the scattergram all at once.
Okay, so we can find the regression line if we want to with our calculator, or in some cases it's given to you the way it is here. So here we have a case where the t is the number of years since the year 1900, and that's the input, and the output is p, the percentage of Americans that smoked cigarettes in that year. So we can use that equation to answer some questions. For instance, we can figure out, we can follow these instructions, rewrite the equation with the function name g. So all we do is replace y with g, well, in this case the input variable is t. So in the previous one we had y equals to negative 0.48 t plus 71, and actually this was a p. So now in function notation, this will be g of t, the input variable, is equal to negative 0.48 t plus 71. So that's the function notation style of writing it. We can evaluate g of 117. G of 117 is going to be negative 0.48 times 117 plus 71. So now we can just use our calculator to evaluate this, 117. So what do you get when you do that? Are you guys getting 14.84? Yes. 14.84. Guys? Okay, 14.84 is what we get. And then how do we translate that into this situation? What does that number mean? This is kittens, number of cigarette boxes. This is, what is this? Dollars? What is this? Percentage of people that smoke cigarettes. Okay, so we can better rewrite that as the year 2017, right? It's 117 years after 1900. It's the year 2017. So according to my model, in the year 2017, 14.84% of adult Americans will be smoking cigarettes, according to my model. Good? Okay. Find the value of t when g of t equals to 30. Okay, so how do we do that? We set our equation equal to 30 and find the value of t. So we'll get negative 0.48 t plus 71. And now we solve for t. So we're going to subtract 71 on both sides and divide by 0.48. So 30 minus 71 divided by negative 0.48. I'm getting 85.4167. Leave it as 42. Round to 2 decimal places. Equals to t. Okay, so how do we translate that? What does this mean? This was what? Was this a year or a percent? Percent, right? So if we tie the whole thing down, we would say that g of the input variable, which is this, 85.42, equals to 30. So this is the year, right? This is the input value was years. So this is referring to 1985%. Okay, so according to my model, in 1985, close to 85 and a half, right? Close to, you know, maybe like June or something like that, halfway through, maybe a little bit lower than that. We'll investigate this in more detail later on. But approximately 1985, about 30% of Americans smoked cigarettes. Good. We can find the p-intercept point. What is the p-intercept point going to be in this case? So remember, traditionally we like to use x's and y's, the x-intercept, the y-intercept. But now we have to figure out which is which. So which one is playing the role of y? Which one is the dependent variable? Which one's the independent variable? So when we have our picture, you know, it looks something like this with a bunch of little things over here, where this is t and this is p this way. So this is the p-intercept point, right? So how do we find it? First of all, how do we find the p-intercept point? We set t equal to 0. Okay, so we have our equation g of t, which would be 0, is equal to negative 0.49? 48 times 0 minus 71. Is it minus 71 or plus 71? Oh, plus 71. Okay, so we get that g of 0 is 71, which means that this point right here is 0, 71, right? And then how do we translate that into our situation? In 1900, 71% of adult Americans smoke cigarettes. That's what this is indicating. Does that seem reasonable?
Yeah.
Maybe. I mean, a lot of them smoke, right? I'm not really sure, but okay. Oh, okay, last one. What is this guy then? How do we find that? We set the output equal to 0. So we're going to take this equation, set it equal to 0, and solve for t. Negative 48 t plus 71. So that's going to give me negative 71 divided by negative 0.48 equals to t. And we get negative 71 divided by 0.48 gives me 147.91 equals to t. Right, so this is the input value. We can rewrite it in function notation as g of 147.91 equals to 0. Right, that's what this is. This is 147.91 comma 0. Okay, and then in terms of our situation, this means that in the year 2040, I mean, we can round it to the nearest year, so that would be the year 2048. No, 0% of adult Americans smoke, so, you know, people will stop smoking by the year 2048. According to my model, does that seem reasonable?
Maybe.
You really think at some point nobody's going to smoke cigarettes?
In a perfect world, yes.
In a perfect world, I think somebody's always going to smoke cigarettes, right? As long as they're around, someone will be cool enough to smoke. So, at any rate, that's how we interpret those two. All right, let's all take a look at this one. So the number of commercial airline boardings on domestic flights increased steadily during the 90s, and then we have a table showing us some results. So 1991, there were 452 boardings, 452 million boardings, right? So 1993, 487 million boardings, and so on and so forth. By the year 2000, there were 666 million domestic airline boardings. Commercial boardings on the domestic flights. Okay, so first of all, we want to create a scattergram. Part A says let f of t be the number of commercial airline boardings on domestic flights in millions for the year that is t years since the year 1990. Use a graphing calculator to draw a scattergram of the data, and then we're good for part B. It says find the equation Okay, so that's something we very often do in this class. Use our calculators to find the scattergram and then the regression line. Okay, so we turn on our calculator. We quit out of whatever screen you might be on and clear. Your main screen is on there. First, we're going to go to Stat, Edit, so hit Enter. Then I want to input my values. So we want to input these values and these values. These are our input values and our output, except we don't use calendar years. So we got to convert it into T values, which are the number of years after 1990, according to this problem. Okay, so I'm going to go over to L1, clear, enter to delete everything below it. L2, hit clear, enter, delete everything below that. Then I'm going to input the values 1, 3, 5, 7, 9, and 10. Right? These correspond to the year 1999, the year 1995. Right? So we're counting the number of years after 1990. That's how we encode these years. And then the output values, the dependent variable, are going to be the resulting number of boardings. So 452, 487, 547, 599, 635, and 666. There they are. So we have our ordered pairs all set up on list 1 and list 2. To create a scattergram, I'm next going to go over to y equals. See how there's an equation on there? It's just going to cause problems. So I'm going to clear it or delete it. So if I hit clear, it'll just delete it. Or if I go over and highlight the equal sign and then hit enter, it'll stop being a dark equal sign. See how it's light now? That means it's been deactivated. It won't try and graph. It will be fine. So you can save it for later. Or if you just want to delete it, we can just hit clear, get rid of it. Okay, I'm going to go to stat plot. So second, y equals, so to get the stat plot. Then I'm going to hit enter for the first one. It's on. That's what I wanted. It's a scattergram, right? We use our arrows to select different things. So in here, for now, we just want this guy. L1, L2, and little plus symbols. That's good. That's what we wanted. Okay, then we can go over to the window and choose a good window for our settings. So see, right now it's set from 0 to 50 for the input values, but I'm really only inputting things from 1 through 10. So that might be a bit of an overkill to go all the way out to 50. And then for the output values, I'm only graphing from 0 to 100. And my output values are from 452 all the way out to 666. It's not going to capture the results. Right? So I can put in some other values myself, maybe like 450 to 700 or something like that. Or the other thing we could do is have the calculator choose a good window for us and then go back and tweak it, which is what I would recommend. So we can hit zoom and then go down to stat. So for most calculators, it's the 9th option down, zoom stat, enter, and then it'll automatically pick a good window for you. So if we go back to window, now we see what it did. The calculator chose to go from 0.1 to 10.9 for the input values with a scale of 2, right? Every little tick mark is counting by 2s, 2, 4, 6, 8. And then for the output values, the calculator chose to start from 415 and all the way up to 702. Again with a scaling of 100. So it's going to count in multiples of 100. Okay. All right, so then we can change that a little bit if we want to, or leave it alone. In particular, if you want to see where the x and y coordinates are, the axes, then you'd want to go back to the window and change this to 0 to see where that is, and then go back to the y minimum and change that to 0 as well. Graph it. It might look kind of ugly, but at least now we see where the x-axes and the y-axes, the vertical and horizontal axes, are in comparison. Okay, so leave it like I'm going to leave it like that. Okay. All right. So now I want to come up with a. I created the scattergram now. That's part A. Part B said find the linear regression line, the line that best approximates all these data points. So remember that in this class we've done a few things. One, I asked you to create a scattergram on your own on paper, and then just kind of eyeball a line that goes through them all. That's something you're asked to do sometimes. Sometimes you might be asked to pick 2 points so that if you find the equation of those 2 particular points, the line that goes through those 2 points, it might make a good approximation. So there is a variety of points that you can choose here, and if you choose two of them and find the equation of the line that goes through those two, then that line hopefully might make a good approximation of the rest. Or the third thing you might be asked to do is to have the calculator choose one for you, a line that best approximates all those points. And that's what a linear regression line is. So I'm going to do that by going to stat, calculate, down to linreg ax plus b, the fourth option down. Then we're going to type in the following information, parentheses, L1, comma, L2, comma, bars, go to the right, enter, and then choose where you want to store the information. Doesn't matter where. Close. Okay, so the first value, L1, is where are the x coordinates, comma, where are the y coordinates, comma, and then where do you want to store your resulting information, your resulting equation. Okay, so that's how we type it in there. Many of you guys have that newer screen where it takes you to a new window and it asks you those things, so just follow their instructions. Where are the x coordinates, L1? Where are the y coordinates, L2? Leave frequency blank. Make sure there's nothing in there, it'll give you something wrong. Leave it blank and then go down where it says store, and that's where you do the vars thing. Vars, go to the right, enter, pick where you want to store it. Then use your arrows to go where it says calculate, hit enter, and you'll get the exact same answer that we're getting here. Okay, so according to my calculator, the linear regression line that best fits those points is a line that has a slope of 24.071 and a y-intercept of 423.9178. Okay, so we can use these two numbers to create a linear equation that best approximates it. If we go over to y equals, then we see that it's already been stored in y sub 3. Here's the slope, x-intercept, and if we hit graph, we see that it already graphs the scattergram as well as the line, and it does seem to be doing a pretty good job of approximating those points. Okay? Remember that, okay, well right now I zoomed out so that I can see where the y-axis and the x-axis is, but if I wanted to kind of zoom back in, I can go back to zoom, stat, the ninth option down, and it should give me a window that's pretty close to all those points, like that. Okay, now we can kind of see it a little bit better. And we can see now that the line doesn't actually go through some of these points. They're a little bit below, a little bit above, but they're pretty close. So it does seem to do a pretty good job of approximating these points, and they do seem to fit a linear model pretty well. Okay, so let me just go back to, for now, let me just go back to this, which is 0 there and 0 here, just so that I can see where the x and y coordinates are located. And if I graph, then I go back to this. That way I can see again where this x coordinate is there and this coordinate is there. Okay, so we have our scattergram, we have our graph including the scattergram points and the line, and if I go over to y equals, I can see the actual equation.
Okay, so back to our word problem then. On our calculator, this was the result, right? This is the equation that went through that line, the equation of the line that goes through those points, or approximates those points, where this is the slope and this is the y-intercept. Okay, now our calculators always work with x's and y's, but many of our word problems involve different variables, right? So in this case, they wanted us to use t to represent the number of years, which is the input value, and then we're going to write it into function notation, right? Part A says let f of t be the number of commercial airline boardings. So in function notation, this would be f of t This is f of t equals to 24.07 t plus 423.92. Okay, so that answers that question. Right, part A said let f of t be the number of commercial airline boardings on domestic flights in millions for the year that is t years since 1990. Use the graphing calculator to draw a scattergram of the data, right? So here we have an equation where we input t, the number of years after 1990, and the answer is something that's a good approximation as to how many domestic flights there were in that year.
right? So we already have some good information, right? This is the real information. So what would happen if I plugged in f of 1? This is saying this is the year 1991, and we put it in here, we get 24.07 times 1 plus 423.92, and we get f of 1 equals 2, so 1 times this plus that's going to be what? 447.99, is that right? Okay, so what is this saying? According to my model, it's a fancy way of saying my best guess, right? It's a guess. According to my model, in the year 1991, there were 447.99, pretty close to 448 million boardings on domestic airlines. Okay, but we know that the real answer is 452, right? So we don't use our model in cases where we already know the answer. We use our model to try and make predictions about calendar years where we don't have information. Good. So there was a question about residuals that we dealt with before. The residual is the difference between the actual amount and the estimated amount. This is our estimated amount. So if you're asked to pick one, you'd go with the actual amount. We know the real answer was 452 million boardings. This is just a guess that's based on all the information in a pattern that occurs. Good? Okay, so we wouldn't use it for that, but we would use it to make estimates about information we don't have. For instance, use your Model F to estimate the number of boardings in the year 2001. The actual number was, okay, so let's estimate it for the year 2001. So in the year 2001, what is the t-value going to be? 11, right? Because we're counting the number of years since the year 1900. So all we have to do is evaluate this function at 11, which is 24.07 times 11 plus 423.92. Alright, so figure out what that is. What's 11 times 24.07 plus 423.92? 688.69? Okay. So 688.69. Can we have a decimal number of boardings? No. However, remember this isn't 688. This is 688 million. So if we wanted to convert 688 million into a number, you know, without, if we wanted to convert that into a number, we'd have to add the 6 zeros that come behind it, right? 688, 1, 2, 3, 1, 2, 3. So we moved the decimal space, which was right there, we moved it over 6 spaces and added those zeros. So this is really 688, comma, 690,123. Right? So 688.69 million is really 688,690,000. Good? Okay, so we're going to accept the decimal here. It's fine. Let's go out to 2 decimal places. It does make sense in the context of this word problem. We're allowed to do that. But if it were individual boardings, you really can't have decimal boardings. You either board the plane or you don't. Good? Okay, so that's what we get for 2001. So a sentence that you might be asked to put together is this. First of all, we started off by saying, according to my model, what? According to my model, in the year 2001, there were 688.69 million. What sounds better, 688.69 million, or to say this, 688,000, 690,000? Depends, right? So this or you can put 688,690,000, either one. There were 688.69 million boardings. Good? Okay, so we answered the question. Use your model, estimate how many boardings there were in the year 2001. Now the second part of the question's entrance says the actual number was only 622 million. What is the error in your estimate? Right, so now that we know the real answer, we have an estimated amount and we have the actual amount. So the error is the difference. The error is the difference between the estimated value and the actual value. Okay? So actual minus estimated is what we want to do for residuals. So the actual value. So error is the actual value, the real value, minus our estimated value. So for 2001, we know there was really 622 million boardings. And I'm just gonna, since they rounded to the nearest whole number there, we can just round that to the nearest whole number here as well. So I'm just gonna round that to 689 for the purposes of this. You'd follow your instructions if this doesn't give you any instructions actually, but on the test or something I would let you know, make sure to round everything to 1 decimal or 2 or whatever, nearest whole number. Okay, so what do we get here? Negative 67. Good. So that's the difference between, so we're pretty off, right? The model is really off. Why is it so off? What happened in 2001? Yes, so 9/11 happened, and maybe that's what affected the number of domestic flights that took place that year. Okay. For the next part it says the error is this, negative 69 million, right? Don't forget that this is in millions. The number of boardings in 2001 was low due to the terrorist attacks on September 11th, 2001. By making the following assumptions, estimate the amount of money airlines lost that year. Okay, that's interesting. So here are some assumptions to take into consideration when trying to decide how much money did they lose due to lower traffic, right? So all trips, make the following assumptions. All trips are round trips. The average number of boardings for a round trip was 4. So most people have a connecting flight. So just assume a trip is you go there and you come back. And for most people, going there means 2 different flights, so 2 different boardings. And then coming back is again another 2 different flights, 2 different boardings. And the average airfare for a round trip is $340. So estimate how much money the airlines lost due to lower traffic in the in the number of boardings. Okay? So what should we do? So this is how much we expected, the number of flights we expected, right? The number of boardings we expected. This is how much we actually got, meaning that we were 67 million boardings short of what we estimated that year. So if we want to calculate about how much money they lost, this is the number we want to focus on, right? 67. Now the fact that it's negative is indicating for you that this one is smaller than that one, right? Okay. We got to figure out how much money there was. If we assume all trips are round trips, so round trip, you go there, you come back. So of the 67 million boardings, if everything was being charged as one direction and you didn't have any connecting flights or anything, then there would be 67 fares But a fare isn't a one direction and not including stopovers. A fare is a round trip. Okay, so most people start in city A, and want to go to city B. And so they pay an average of $340, right? On average, that's how much people pay. But that includes going over to a stop, some other place they don't care about. Hello, Phoenix. And then you go that way, right? Okay, so 1 flight, 2 flights, and then maybe you go back to that one and that one, and you go back that way. So there's really 4 different boardings that happen, right? This 67 million boardings includes the fact that on average people do 4 boardings for just 1 trip, where the trip is $340 on average, right? So what should we do to this 67 million?
Divided by 4.
Divided by 4, and that'll give you how many trips, right? So these are boardings, and we want to figure out how many trips there were. A trip being a round trip. Okay, so we take the 67 million and divide it by 4, and what do we get?
16.75.
16.75, that's still in million. But now it's trips. Right? Round trips. Round trips. Round trips. Good? Okay, so now what do we do with that?
Multiply it by the 340.
Now you multiply by the typical price each round trip fare is. So we multiply 16.75 times $340. And what do we get?
5,695.
5,695? Yes?
Yeah.
What do we do there? A million?
Yeah.
5,695 million. It sounds weird, right? What happens when we're talking about millions? You know, we get to 800 million, and then we get to like 987 million. Okay. And then what happens when we get to 1,000? Do we describe it as 1,200 million?
No.
What do we say then?
1 billion.
Billions, right? So 1,000 millions equals 1 billion. So 1,000 millions is equal to 1 billion. Okay, so you can describe it this way. I would accept that. I'm not going to penalize you if you gave me the answer this way. So airlines lost an estimated $5,695 million. Or you can write it as $5.695 billion. Or you could just go back to writing out the whole thing, right? We add the extra 6 zeros there, so it'd be 5,695 and 1, 2, 3, 4, 5, 6 zeros. That much. Okay, so $5,695,000,000 dollars is the estimated amount of money that they lost due to lower traffic that year. Any questions? No? 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 One last thing, if we go back to our equation. If we go back to our equation that we got from our calculator, we got that, what are we using, f of t? F of t equals to 24.07 t plus 123.917, right? So there was our equation. Just as a rough sketch, what we had was this. These were t values, which was the number of years since 1990. Number of years since 1990. So we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, something like that. And then in this direction, we had number of boardings in millions. Boardings in millions, so we had f of t in this direction. And so we had pretty big numbers already, kind of like this. Something like that. And we had this line that kind of went across that way. Okay, so first question, what is this point right there? It's the vertical intercept, right? Traditionally the y-intercept. But what numbers is it? From our equation, I can tell that it's that guy. 0, 423.917. Right? Because if we input a 0 in there, then this whole thing becomes 0, and we just get that guy. Okay? And what does it mean in terms of this word problem? What does this mean?
1990 or that maybe.
According to my model in 1990, right? 0 years after 1990 is going to be 1990. So according to my model, there were 423.917 million boardings that year. Okay? What's another good question? What is this? What's a good sentence to describe the 24.07? The slope. How can you describe the slope? Well, it's the rate of change of the line, right? So slope, which is equal to 24.07. Well, we can just turn it into a fraction by doing this, 0.07 over 1. So we can do it that way. We could leave it like that, or we can multiply the numerator and denominator by 100 to move the decimal over 2 spaces. So we get 2407 divided by 100. Right, just to get some nice numbers on there. And then either way is fine. And then you can talk about the rise over the run. And then think about what kind of a thing is the run and what kind of a thing is the rise. Okay, so this is nicer in terms of getting some nice whole numbers, getting rid of the decimal. But sometimes it's kind of an ugly interpretation as well. So you can also leave it this way. Run, rise. So the run, what kind of a thing is it? It's years, right? Years since 1990. And what kind of a thing is the rise in this case? Well, it's boardings, right? Boardings in millions. So if we pick a triangle anywhere on here and we go exactly 1 unit, then I know that I'm going to go up by 24.07 units, right? Or if I pick a really big triangle, and this won't be up to scale, but if I pick a big triangle and I go out 100 units that way, I know I'm going to go up 2,407 units that way, right? And this isn't to scale, because this is 100 years later, this is going to reach all the way out to 2090. But if I do a big triangle, this will be 100 years this way, and 2,407 that way, right? That's how we can interpret these fractions. Okay, but let's stick to the smaller fraction for now. So let's come up with a sentence of what this means. For each
year after 1990,
there
is a rise in flights of 24 million.
24.07 million,
Yeah.
right? We could just round it to 24 just to make the sentence, you know, a little pretty. So the slope indicates that for each calendar year past 1990, the number of boardings increases by 24 million, right? That's a interpretation of what the slope means in this case. Good. So a slope of, let's say, 24, approximately 24, means that for each year, it's not, for each year after 1990, the number of boardings increases by 24 million. For each additional year. Every single year, for each incremental 1 year period of time, the number of boardings goes up by about 24 million boardings, right? A sentence using this thing, if we wanted to keep it, would say that for each time span of 100 years, the number of boardings would increase by 2,407 million or 2.407 billion number of boardings. Good? Questions? Comments? Issues? No? 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 Okay. So we can also use this equation to find out other things. According to my model, when did the airline industry begin? When were there the first boarding or 0 boardings? When did it all start? According to my model. The model is consistent. How do we figure that out? Right, there could be some word problem. You know, it could be phrased in a variety of ways. When did the airline industry first get started? When is the first, when was the first inaugural flight? When did people start flying airplanes? Right? There's all kinds of ways of asking it, but what they're really asking you is, in which calendar year was the number of boardings equal to 0? So we really want to kind of extend this down and go, okay, it's somewhere over here, right? It's somewhere before 1990, which means that the independent variable is going to be negative. Negative values are okay in this situation. If you get -3, what year would it be? 87. If you get, right? So according to my model, let's figure out when this guy is going to be over here. When is it going to reach 0? Well, how do we do that? We want that to be 0 or that to be 0. Do I let the t equal to 0? T equal to 0 is right here. No, we want the f of t to be 0. I want the answer to be 0, right? So, to figure out where that t-intercept is, we're going to set 0 equal to 24.07 t plus 423.917. Right? So bring over the 423.917 and divide by 24.07. We get negative 423.917 divided by 24.07 equals to the t. And what do we get in that case? Negative 30 people with a calculator. Negative
17. Wait, well, 61. Yeah.
61 point.
Negative 17.61.
Wait.
Negative
17.61. Yes? Okay. Equals to t. Alright, so we can round that to about 18 since we're doing calendar years. Or we could say, about halfway through. So 17 and a half years prior to 1990. So what calendar year are we talking about? So if it was, between negative 17 and negative 18, right? It's somewhere in there on the number line. So if we go back over here, here's negative 17, negative 1, negative 2, negative 3. We're going to run into negative 17. And then afterwards, here's negative 18 over here. So somewhere in the middle there is where we want to be, somewhere in there. So what calendar year would this guy be?
73.
1973. And this guy is 1972. So according to my model, somewhere between, well, it's the year 1972, isn't it? If it's between those, then it's the year 1972. Okay, so according to my model, in sometime during the year 1972 is when the first boardings occurred, when the airline industry started. Good? That's what that means. This is the ordered pair negative 17.61 comma 0. So the math model gives you that. But does that make sense? Is that when the first airlines took off? 72. No, I know you're all young, but no, there were airplanes before then, and there were airlines before then, and so clearly not good. And so you would say what?
The model's broken.
The model has broken down, and it's broken down because why? Why is it obvious that it would break down? Because there's a ginormous gap between this year and the real one, the first known data point, right? The real known data points are in the 90s, right? And now we're doing extrapolation. We're trying to use our model to go really far back before the last real known data point. Lots of stuff could have happened in this time span, and so maybe it no longer followed the linear model, right? So models are typically only good for a certain segment of the input values, and then they fail, right? It's going to give us a silly answer going that way too, right? Because it's going to grow on forever and ever and ever and ever and ever. Do you guys think that the number of boardings on airplanes is going to continue to grow non-stop forever?
No.
No. At some point, it's probably going to maybe level off or maybe go down. Maybe we invent a new form of transportation that, you know, starts to slow down the number of boardings on airplanes, right? Maybe we get those hyperloops going, and there's like awesome trains that go all over the world, and the number of people on planes starts to decrease, right? Or maybe we develop teleportation. You just go on a thing and teleport someplace else. So then who would get on a plane? Who knows, right? So the model is only going to be good for a certain segment of the domain, and you have to make note of that. So you find the real answer, and then you just make note that, you know, clearly the model has broken down. But according to my model, this is what it tells me. According to my model, airline industry started in the mid 1972-ish, but obviously that's not right. Good? Any questions?